For this session, I think we go through a little bit for the decouple idea to solve this kind of question. So I believe you already have some concept, which is why we should need a forward kinematics and how can we derive the equation for that. We must derive it from the DH form they already give to us. Okay, they are all the parameters for each joint. We need this kind of information. Today, in class practice, we will also give you a DH parameters. Then you need to compose into a question, a program that you can use in your midterm exam. If you finish that, okay, today we will have an in-class practice. You will submit to the internet, but for the week 10, then you can bring your source code with you and try to help you to solve the question or a problem I provide to you. I think that will be the not compromise, is must to have tool, I would say. Okay, so for the chapter 5, the inverse kinematics, we assume be given the position and the orientation. Like this, we have the final position and the final orientation in 4x4 matrix. But how can we come out the final joint angle we need? Because we need a joint angle to control our robot can move to somewhere, the final destination. So this is one of the target we will introduce in this chapter. Okay, so I think we stop here last week to explain to you that it's very difficult, and if you want to solve this equation, it's almost impossible. Okay, so we will go to the kinematic decoupling, and we separate. I jump a little bit quick because we already introduced. I just review for this session. We decouple we assume our robot has a 6 degrees of freedom. So for the first 3, we call it as a joint frame or joint kinematic. And for the last 3, we call it as a wrist, W-R-I-S-T, wrist kinematics. So by decoupling by this way, it can easy is a verb. It can easy our computation. Okay, so this is the exactly the procedure we will use. We decouple the last 3 joints. We call it wrist. I mentioned it before. I always use the same term. If I change it a little bit, remind me. I don't want to do that. Okay, so the last 3 joint we call wrist joint. We decouple it from the first 3. Okay, so this is the independent kinematic system, and we will adapt some information. The first information is I was supplied for the final position and the orientation. Okay, and we know the last 3 wrist joint is they will intersect in only one point. We call it as a O6. Okay, and this O6 is what we need to pursue. Once we find out the O6, or we call the joint intersect for the rest kinematics, then we can solve the last 3 joint position right away. Okay. Over here, that is the very crucial equation you need to understand. Okay. For the final equation or the matrix array over here is what you need program into your MATLAB program. Okay. Because we need to have XC, YC, ZC. Where is the C point? The C point is the rest center. Okay, we mentioned about rest kinematic, but what is the center for the rest coordinate? That is XC, YC, and ZC. We need this information, and we can get the information because we have the original OSOYOZ. OSOYOZ is provided by the user, and I will provide to you. And also, I have the length for the D6, which means it's the joint center to the end effect. Yes, I will provide it to you. So eventually, this is no information, this is no information. But how about the R1, 3, 2, 3, and 3, 3? It's a vector, and also provided in the information I give it to you. For the first page, over here is the rotation matrix, or we call orientation matrix. So the R13, R23, R33, you need to locate where it is in the matrix. Then you need to adapt the value into our equation to find out the rest center. Okay? I believe it is very straightforward. Yeah, very straightforward. So if you know how to use the hand calculation, then I would say it would be fine for you to do the programming. Of course, I am saying you can use the MATLAB to code, to solve your question in the midterm exam. If you want, you can also use the handwrite. I'm okay. I'm okay. Yeah, as long as you can provide me the final answer, that will be fine. I'm okay for that. But I'm just trying to say, use the code to help you will be easier. Yeah, definitely, of course. But here is the theory, and we introduced last week why the final equation become by this way, because we go through the whole part. Then they have the vector and the matrix multiplication. Then you can see the final result is easier. So I would say for the inverse kinematics, it's just a mission. Where can you find the final formulation for your answer? So we already obtained our rest center position. Any question so far? So okay, I mark with the rest center final position. Okay. Over here, I think this is just supplementary for how can we get a final result for the rest center. So we should go further a little bit. Okay. So for the inverse position for I'm not sure. Yeah, for the first three, okay, we decouple it. Okay, and eventually we have rest center be located. Okay, we can calculate from the final position we already give to you and go to the rest center. Then how can we compute the first three angle, which is theta 1, theta 2, and theta 3. Then we apply this geometry. Okay, so when you use the projection, 投影, you use the projection to project on your floor plane. Then you can have an angle with, because you have an XC, So you can project, because in this spatial position, but it's not be called position, it's called posture. Then you can project onto the xy plane. Then you can obtain the xc and yc immediately. Then you can find out the theta 1. You can find out the theta 1. Then we have other information, for example, the r. Okay, I can exactly know this is a joint 0. We don't have a joint 1. So the last joint we call joint 5. And the final point called 6. Okay, so this is a joint 1. And they have another projection for onto the ZC projection. So eventually, is a kind of, they mentioned a geometry method. So you use the projection, this kind of tool, then you can find out the theta 1 and theta 2. Okay, so this is a more detailed explanation, but as I mentioned, okay, they have a lot of condition. Let me jump a little bit quick to somewhere. But over here is okay. For theta 1, I already inverse it. Okay, for theta 1, we use the attangent tool. Did I reverse it? Let me take a look. Yeah, I think I reversed it. Okay, so you have a xc and yc. We just find out in the front, and we can come out the answer. And there's another issue is for the cosine and sine value. It is a little bit tricky because between the 0 to pi and 0 to negative pi, they have different value. So if the answer come out is not correct by comparing what you input, then it may be in the other phase. Okay, so in this case, they mentioned over here the other validation solution for theta 1 maybe is the original data plus pi. Okay, so that is the arctangents issue because we need to find out where is the exactly solution. Stop over here, we can think about this. For one position and orientation matrix, you may find more than one solution. That's normal. That's normal. So that's another issue when we program the control code for robot. We need to validate if this angle is reasonable or not. What is reasonable or not? Yeah, because when you move to start point, if your answer is jump to the other pi, then you must recognize this is not the reasonable answer I should use. Because if you use the robot control may have the very rapidly motion. Maybe when you want to move A to B, maybe they will move from A and have a large motion in between and go to B. That is what we don't want. Okay, so it's an easy programming question, but for the practice use, there are still a lot of issues you need to face. Of course, right now the international brand, I believe there is nothing. They will not allow this happen in their system. But for some homemade system, especially made in from university, then you may have this kind of situation. So I need to remind you, yeah, you need to always double check if this is the reasonable answer for the next step, or you will have a very big swim in between. Then they will maybe collide with some other equivalent. That's not good. Okay. So for the offset issue, we discussed later. Okay. In this case, our offset is equal to 0. Okay. But for the case over here, remember we have this is theta 1, right? Okay. we have the theta 1 already, but if we have an offset, then the whole equation will become more complicated. So you need to retreat somehow from here to perform the calculation. I forgot our case. Our case may skip the offset, but when we face the question, I will let you know. Okay. So in the previous slide, we project on the XY plane, but for this case, we project on the Z plane, but no matter where it is. Okay. In this case, we try to find out what is the theta 2 and theta 3. Over here, you can see more clearly, yeah, because you use the law of cosine, you can find out where is our theta 3, okay? Then eventually we will have the final answer, which is the arctangent 2D and 1 minus D2 or something like that. And of course the theta 2. Okay, I don't want to go to the more detail. Then you can take a look, but eventually you need to know how to program into your code, okay? And over here, I believe I try to demonstrate something, because there is another type called Stanford robot. And the rest station, I try to mention the rest station is the same, but for the first 3 it's different. So you need to observe from the DH form or DH parameter I provide to you. Okay, so I'm saying over here is for the Stanford compared to RRR. You don't remember what is RRR? RRR means all articular robot. So it's all revolute joint robot. But for the Stanford, you don't need to memorize that, but I just want to show you. The first 3 joint is a little bit different. They have a prismatic joint for that. But the last 3 is all revolute. So it's the same type. No, not same value, same type. Okay, so they don't have AI, because AI is offset, I think. And for the first one, it's different. Okay, for the first 3, 1 to 3 is different compared to the RRR. I think that's what they try to say, okay? So yeah, I just want to mention in this slide. Okay, should be fine. But Stanford, I think I will not give this kind of robot to you. I will provide you the very famous one, okay, the most famous one, because we don't need to worry about the arm design right away, because we just manufacture the arm type like our human arm. They will be fine, because the human rod is also have a 2 arm, and the 2 arm is exactly the same like a human arm. Okay, so we just go for the type, will be fine. And easy complicated. I forgot what is the meaning for that, and I believe I obtained the rotation matrix from 3 to 0 and 6 to 3, and the final answer is by this way. I think it's from the previous slide. So you have to use your MATLAB program to do that. And as I mentioned, in the midterm exam, you will have a complicated answer. So remember, copy and paste it onto the PowerPoint, then give the answer and mark which answer belongs to which question, then you will be fine, okay? And here is some trigonometric function you may use, or of course, but I'm saying you cannot check it online, so yeah, don't do that. But if you check online, I believe there is no answer for that, okay? Not this one, it's from my question, okay? So over here, I just go more detail for the part, and I forgot why should I do that, but I think I just try to tell you, if I want to find out the C4, S5, this value, where can I obtain the number? I almost retrieve everything from the textbook. So for the result or for the highlight, I believe you can use, I forgot where it did it come from. Okay, so yeah, I think this is a little bit weird to me because I explained the Euler angle solution for this session. Yeah, I forgot. So let me recall my memory back, then we can see that. Okay. Here is the equation you need to build up in your program. We have all the 6 degrees of the formula. So I will provide the DH parameter to you, and you will come out the forward kinematics. Then I will provide another angle, no, parameter, no, not angle, sorry, is the final position and the orientation to you. Then you need to find out each angle for the robot in that position. And the answer is not the only one. So you may need to list all of them, okay? So here's the formula. So I'm saying this part is easy because if you only deal with the RRR type, over here, you call elbow, manipulate. Elbow means all RRR robot, okay? So eventually you will have all the formula over here. What you need is this slide, okay? So try to find out where it is. Then I think you will be fine. And today I will let you to do the calculation once, then you will find out what's going on, okay? Here is the type I will provide to you. Don't worry about this part. Eventually, in the future, you will only have this session. But before the design, you need to design your robot by yourself. No, I'm not saying in this case. I'm saying in the industry. So you design a robot, and you come out the DH parameters. So over here, I just want to show you. Here is the parameters for it, okay? And this is the exact equation I will provide to you. Let me explain a little bit. For the joint 1, they have an alpha angle and the length d, okay? And the alpha is, I believe, is they call twist, right? So you can observe the twist is always a negative 90 degree or positive 90 degree, because the twist angle, if you can recall your memory, is offset with the z and the y axis, x-axis, okay? So it depends on next joint. The next joint is belong to which one, and then you will find out the answer, okay? So I will provide to you, okay? And for the theta is the input angle, right? Okay, so you may ask for the forward kinematics first, to find out the forward kinematics first. Then I will provide you a, where is that? Oh, this is another one. What's that? Let me take a look. Later still don't have any stuff. Okay, I think I just want to collect the information for this one. Okay, so once you have your forward kinematics, then I will provide you the final position for you. Then you find out the angle and you already have position. So just find out a joint angle. Yep, it will be fine. Okay. Yes, yeah, another type. Okay. Yeah, I tend to collect a lot of joint, yeah, for explanation. Okay, for this part, any question? I will upload to the internet. Don't worry about it. Yeah, because that's what I collect. Okay. Actually, upload the PDF is very illegal. But I buy 10 books, so I think they will forgive me. Yeah, but I would suggest you to buy one if you want to devote yourself into this field. Okay. Any question so far? I believe it's last time, not last week. It's a long time ago. Last time we stopped in forward kinematics, right? So today we will continue to do that and provide you, because you need to build up this one for yourself and find out the final position, final joint for that. Okay. At this point, do you understand what I'm saying? Okay. Forward kinematics, I believe you guys are okay. Okay. For the big wall part, big wall, inverse wall, I will provide the edge for you. Then you find the angle. The angle over here, you just, okay. So you need to compute the angle with the formula, whatever it comes from. Okay? Question? Yeah, I think this is easy one, okay.